Welcome viewers to the third segment of the first lecture for the online series of lectures for the course of Algebraic Topology 1. In the last segment, we stated theorem 1 for the path homotopy classes and the product between them. So we start the proof of the theorem in this segment. Okay, so the proof depends on two key facts. So let me state the two facts. If k from x to y is a continuous function, and f is a path homotopy in x between the paths f and f prime, okay, then k composed with f is a path homotopy between the paths k composed with small f and k composed with f prime as maps from I to y, okay, and this path homotopy is in y, big Y, okay. So let me draw a figure for you. So this is I cross I unit square, okay. Say this is x, and under f this edge is going to be mapped to this path between two fixed points, which is f prime, and this edge of I cross I is going to be mapped to the path f in x, okay. This is the homotopy, path homotopy. Now this is another topological space y, and there is a continuous map k from the topological space x to the topological space y, and under this continuous map these two paths are mapped to the paths k composed with f prime and k composed with f between two fixed points, okay. And this path homotopy, the path homotopy between these two paths in y is k composed with big F, okay. All right, so this is the first fact. I'm going to prove the first fact now. So since f is path homotopic to f prime in X, we have a path homotopy f, a continuous function from I cross I to X, right? So that big F of S comma 0 is small f of S, and big F of S comma 1 is equal to F prime of S, right? F and F prime are homotopic. Now the fixed points, the initial and the final points. The initial point is going to be f0 comma t is equal to x0 for all t, and the final point is f1 comma t, which is x1. Okay, so the initial point between the two paths for the two paths, both for f and f prime, the initial point is x0 and the final point is x1. Okay, indeed one has K composed of with big F at S comma 0, just composition of K on both sides will lead us to K composed with small f evaluated at S on the right side, and K composed with F evaluated at S comma 1 is K composed with F prime evaluated at small s. Similarly, K composed with big F at 0 comma t is equal to K at x0, and K composed with big F evaluated at 1 comma t is equal to K of x1. Okay, so straightforward composition with K gives us these conditions. Now one immediately sees that since K from x to y and F from I cross I to X are continuous maps, their composition will be their compositions their composition K composed with F from I cross I to Y is continuous as well, right? Therefore, and so this is a continuous map, and uh, this continuous map satisfies these conditions. Therefore, K composed with F is a path homotopy. K composed with F is a path homotopy between K composed with small f and K composed with F prime in the topological space Y. Okay. Okay. So we are done checking the first fact. Now I'll state the second fact. The second fact is that if K from X to Y is a continuous map and if F and G are paths in big X with F of 1 is equal to G of 0, it means that the final point of F is the same as the initial point of G. Okay? Then the following holds. K composed with F star G is equal to K composed with F star K composed with G. Okay? So let us quickly check this fact. Okay, so indeed, for continuous maps, F comma G from I to X. Okay, since F and G are paths in X, and X0, X1, X2 in X, such that F of 0 is equal to X0, meaning that the initial point of the path F in X is X0. The final point of F is X1. The initial point of G is the same as the final point of F, which is X1, and the final point of G is X2. Okay. So one immediately sees that F star G makes sense. Okay. F star G makes sense as a path in X with F star G at 0 is equal to X0 and F star G at 1 is equal to X1. Sorry, is equal to X2. Okay. The final point of F star G is the final point of G, defined by F star G at S. It's our old definition of the product between paths. F of 2S when S is in this interval and is equal to G of 2S minus 1 when S is in this interval. Okay, this is how we define the product between two paths, as we already know from the previous segments. Hence, K composed with F star G F star G is a map from I to X, right? It's a path. And K is a map from a continuous map from X to Y. So K composed with F star G is a map from I to Y, right? And this is a path with K composed with F star G evaluated at 0. That's the initial point of this path, which is um, which is we have seen that f star g at evaluated at 0 is x0. Okay, so k composed with f star g evaluated at 0 is going to be k of x0. And k composed with f star g evaluated at 1 is equal to k of x1. Okay, and that this map is given by k composed with f star g at s is equal to, so I'm just composing k on both sides, is equal to k composed with f at 2s when s is in this interval, and is equal to k composed with g at 2s minus 1 when s is in this interval 1/2 and 1. So this is how this map is defined, k composed with f star g. Okay, so I need some space. Let me erase the top part here. Now since k from x to y is continuous, one obtains continuous k composed with f and k composed with g from I to y. Okay, since k is a continuous map from x to y. Okay, with k composed with f at 0 is equal to k of x0, since f of 0 is x0. The initial point of f is x0, so by composing with k on both sides we get this. Okay, and k composed with g at 0, sorry, I should state the final point of k composed with f first, and k composed with f at 1 is k of x1, right? Because f of 1 is equal to x1. By composing k on both sides we get this. Similarly, k composed with j at 0 is the same as k of x1, since g of 0 is x1, and k composed with g evaluated at 1 is going to be equal to k of x2, right? Since g of 1 is x2. So that um, this is the same as this one, so that this makes sense, right? K composed with F star K composed with G. Why? Because for these two paths in Y, the final point of K composed with F is the initial point of K composed with J, so that their product makes sense. This makes sense to be a path in Y from kx0 to kx2, k of x0 to k of x2, defined as, we have our usual definition of product of paths, and using that we can define the product of these two paths in Y evaluated at S is equal to K composed with, so yeah, K composed with F at 2S. Okay, so this one, this function, this map, or which is a path, this path evaluated at 2S when S is in this interval, and the product is equal to this path evaluated at 2S minus 1 when S is in this interval. Okay. Okay. So now compare. So we numbered this earlier equation by 8, and we numbered this equation as 9, as in the lecture notes, and we see that they are the same. So from 8 and 9, we conclude that K composed with F star G is equal to K composed with F star K composed with G. Okay, so this is how we check the second fact. So these are the two facts that will be required to prove our theorem 1. Now we proceed to prove theorem 1. Let me erase everything. We have all the machineries to prove theorem 1. So we'll start with part 2. For the left and right, existence of the left and right inverses. So we proceed to prove theorem 1. Okay, so first we take E sub 0. Let E sub 0 denote the constant path in I, that is E0 is a map from I to itself. Okay, so usually we have a path in a topological space X, and that is a map from I to X. In this case, our path is on the topological space I. So E sub 0 is going to be a map from I to itself. So with all of I being mapped to a single point 0 in I. Okay. So this is one map that we'll be concerned with, and now we denote by small I the identity map from I to itself, and it can also be considered as a path on I. The identity map it is also a path in I. Okay, so how do we define this identity map? I of S is equal to S for all S in I. Okay, and how is this a path in I? So you see that I of 0 is equal to 0 since I of S is equal to S, and I of 1 is equal to 1. Therefore, I is a path in I, big I, from 0 to 1. Okay, so E0 is a path in I from 0 to itself, and small I is a path in I from 0 to 1. Okay, so it makes sense to take the product of E0 with I. Okay, because the final point of E0 is the same as the initial point of I. They are both equal to 0. So we can talk about the path E0 star I from I to itself. It's a map from I to itself, and it's a path in I. Is a path in I from what is the initial point of E0? The initial point of E0 is 0. Okay, so it's a path from 0 to what is the final point of I? I of 1 is 1. So E0 star I as a map from I to itself is a path in I from 0 to 1. Okay. And from our definition of the product between two such paths in I is given by, so is equal to E0 or evaluated at 2s when s is in this interval, and is equal to I of 2s minus 1 when s is in this interval. Okay. And from the definition of E0 and I, E0, well, E0 is a constant map, right? So E0 at S is equal to 0 for all S in I. That is how E0 is defined. So E0 at 2S is going to be 0 for all S in this interval, and I of 2S minus 1 is going to be 2S minus 1 because I is the identity map, right? When S is in this interval. So this is the product. Now it's convenient to have a look at the graph of this product, for which I draw a picture here. Along the x-axis is S, and along the y-axis is U. U is a function of S. Okay, so we are considering linear maps here. So the square is required from 0 to 1 here, and along the U direction we have 0 to 1, and we construct this square. Okay. So this is the final point, and this is the initial point, right? So and we know that I of S is equal to S, the identity map. Okay, so this is just a straight line going through the origin, making an angle of 45 degree with the x-axis. This straight line represents the identity map, right? This is U equal to I of S. Okay, the linear map, and this piecewise defined map, the product of E0 and I is 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 defined as is equal to 0 as long as S lies in this interval from 0 to 1 half. So from 0 to 1 half, this is a horizontal line lying on the S axis, and from 1 half to 1, it is this line y equal to 2x minus 1, right? Which is represented by this line segment. Okay. So this path starting from 0 ending at this point 1 1 is the path U, which is equal to E0 star I at S. Okay. And this path is U equal to I of S, right? So the description of the figure is the map I and E0 star I. Okay. Okay, good. Now I'm going to prove that these two paths drawn in the figure, I and E0 star I, are path homotopic. Okay. Um, I just need to show that there exists a continuous map from I cross I to I, um, given by a G of S comma T, okay, such that G 0 comma, sorry, I have to construct a continuous map from I cross I to I, such that a G S comma 0 is equal to I of S, and G S comma 1 is E0 star I at S, and I have to show that G of 0 comma T is well, it what are the initial and the final points of these two paths? The initial point uh, uh, is 0, and the final point is 1, right? And g of 1 comma t is 1. This is what I need to prove. Okay, and the claim is that g defined by g of s comma t equal to 1 minus t times I of s plus t times E0 star I at s is a path homotopy between I and E0 star I. Okay, that is, it is a continuous map and it satisfies these two conditions for path homotopy. Then we are done proving that indeed these two paths are path homotopic to each other. Okay, I need some space, so I think I'll erase this part. I won't need it anymore because I need this formula for the product of the paths. Okay, let us check what. So from this formula, gs comma 0, I plug in 0 here for t, and I get just I of s straightforward, and g of s comma 1, I plug in t to be 1 here, then it goes away. We are just left with E0 star I at s. Okay, so this first condition is checked. For the second condition, we take g 0 comma t, which is equal to, so I plug in s to be 0 here only, so I have 1 minus t times I of 0 plus t times E0 star I of 0, right? So I of 0 is going to be 0 because I is the identity map, so this goes away, and E0 star I at 0, so this formula holds, and E0 of 0 is again 0 because E0 is the constant map mapping everything to 0 in I, right? So this also goes away, we end up with 0. Now g of 1 comma t is, I plug in s to be 1 on the right side, then I have 1 minus t I of 1 plus t E0 star I at 1, and I is the identity map, so this is 1 minus t times 1 because I of 1 is 1, and E0 star I at 1, this formula holds, right? And this is t times this is t times 1 again, because 2 times 1 minus 1 is 1, so that we have 1 here. So we are done proving the second condition as well. So indeed I is path homotopic to E0 star I. Okay, good. So now I can erase everything. So we have just proved that we'll need the fact that I is path homotopic to E0 star I. Okay, we'll need this result. Now let F be a path in X between x0 and x1, which means that F is a continuous map. F is a continuous map from I to X such that F of 0 is equal to x0 and F of 1 is equal to x1. Okay, from the definition of a path. Now, since I is path homotopic to E0 star I, in I with big G, the way we defined earlier, big G. Okay, with big G being a path homotopy between them. Remember that we defined GST as 1 minus T I of S plus T times E0 star Y at S. This is how we defined the big G, okay, a while ago. So that G is a path homotopy between these two paths, okay. So given this data, by the key facts discussed in the beginning of the proof, in the beginning of the proof, we see that F composed with G, big G, is a path homotopy, between F composed with I and F composed with this guy, F composed with E0 star I. And specifically by the second fact, this guy, the second key fact, gives us that this guy is equal to F composed with E0 star F composed with I. Okay. Now, we know that F composed with I is simply F, since I is the identity map, and F composed with E0 evaluated at S is equal to F composed with is F of E0 of S, right? And E0 of S is 0, since E0 is the constant map mapping everything to 0, and F0 is X0, the initial point of the path F. Okay, and by the definition of this constant path mapping, which maps all of the interval I to the point x in the topological space X. This is nothing but E of x, E sub x0. Okay, E sub x0 at S, which means that it's going to map everything to the point x0 of the topological space. So we have found that f composed with E0 at S is equal to E sub x0 at S, which means that f composed with E0 is nothing but E sub x0. Okay, so f composed with G is going to be a path homotopy between f composed with I, which is f, and f composed with 0, f composed with E0, which is E sub x0 star f composed with I, which is f. Okay, so using the key facts we get here. Okay, so now using the well-definedness of the product between two paths uh, in the respective homotopy classes of paths that we have discussed earlier, that if you have two homotopy classes of paths and take the product, then the resulting class will be the class of the product of the respective paths. Okay, so using this we immediately see that E sub x0, the class of E sub x0 star the class of f is equal to the class of E sub x0 star f is equal to the class of f. By using this, we just replaced E sub x0 star f with f here to obtain this. Therefore, E sub x0 star the class of E sub x0 star the class of f is equal to the class of f. Okay. Okay, so important thing to note here is that ex0 star f is a path from x0 to x1. Okay, good. Okay, now one can go on similarly to show that this identity holds. The class of f star the class of E sub x1 is equal to the class of f. So this is the right identity, and previously we proved the uh, uh, equality for the left identity. This is what we proved earlier. Okay, good. So we just proved part 2, right and left identities of theorem 2. Now we proceed to prove 3. Okay, let me erase everything. To verify 3, first note that the reverse of I denoted by I doodle is defined by I total of S is equal to 1 minus S. Okay, so the definition is given in the statement of the part 3 of theorem 1. Okay, now since I is a path, we have already seen that the identity map I is a path in I, big I, beginning at 0 and ending at 1. Okay, I doodle, the reverse of I, is a path in I beginning at 1 and ending at 0. It's immediate. So it makes sense of the path I star I twiddle, right? Because the the final point of I is the initial point of I twiddle. So this is going to be a path from 0 to itself. Okay. Okay, which is, and from 0 to itself, a path from 0 to itself is the constant path, E0 in I. Okay. Okay. Now, okay. So now we have this thing I star I twiddle is path homotopic to E0 in I. This is a claim. Okay. So this guy is a path from 0 to itself, and so is the constant path E0. And this is the claim that these two paths are path homotopic in I. And it's easy to check. Just take this function h from I cross I to I such that h of s comma t is equal to 1 minus t times I star I twiddle at s plus t times E0 of s. Then one immediately sees that h of s comma 0 is equal to, plugging in t0 here. So this is just I star I twiddle at s, and h of s comma 1 is going to be, this cancels, this goes away, and what we have is just E0 of s. Okay, and we got to check the other two extremes. H of 0 comma t is going to be 1 minus t times I star I twiddle at 0 plus t times E0 of 0, and this is going to be equal to 1 minus t times, what is I star I twiddle at 0? Well, I need a bit of space here to give the definition of I star I twiddle. So let me make some room here on the right hand corner. Hopefully I did not erase anything important required in the proof. Okay, so this is the definition of I star I twiddle evaluated at s. This is going to be equal to I of 2s when s is in this interval, s belonging to this interval, and this is equal to I twiddle 2s minus 1 when s is in this interval. Okay, good. And so I star I twiddle at 0. Okay, so what is this? This is the identity map. So this is going to be 2s when s is in this interval, and from the definition of I twiddle, we see that I twiddle at 2s minus 1 is going to be equal to 1 minus 2s minus 1, which is 2 minus 2s, right? This is when s is in this interval. Okay, so using this definition of I star I twiddle at s, we get I star I twiddle at 0 being equal to just 0, because we are applying this formula for s equal to 0, and well, E0 at 0 is simply 0 because E0 is a constant band. So this is 0, so everything goes away. Okay, so now now the h at 1 comma t is equal to 1 minus t times I star I twiddle at 1 plus t times E0 at 1. Okay, now this is equal to 1 minus t times I star I twiddle at 1. So I'm going to apply this formula now, because 1 is in this interval, so this is going to be 0, right? This is going to be 0, and and this is 0 as well, because E0 is the constant mapping everything to 0, so this is 0. Okay, this makes sense because the initial and the final points of I star I twiddle is they are both 0, right? Why? Because you see that I is a map from 0, I is a path from 0 to 1, and I twiddle is a path from 1 to 0. So I star I twiddle is a path from 0 to 0. So is E0. Okay. So the two endpoints being 0, both of them being 0. Okay. So H is a homotopy between these two paths in I. Okay, so they are homotopic. Okay, so let me quickly draw the picture of these two paths. Okay, so I need some space. Let me create some space here now. I'm done with proving that they are homotopic, but we need to see them with the help of graph. So in this direction I have S, and in this direction I have U as a function of S, and then as usual we have this square uh, of unit length. Okay, and while I'm trying to draw E0S, okay, we are trying to draw these two paths here. The graph of this path here. E0 is just the horizontal line lying along the s-axis. Okay, so this is u is equal to E0 of s. Now for this path, uh, as long as s is between 0 and 1/2, I have u to be equal to 2s. Okay. And when s is between 1/2 and 1, I have that straight line, which is this straight line. Okay. You immediately check that when s is equal to 1/2, s is 1/2, we have u to be equal to 1, right? And when s is 1, we are going to have this guy to be 0, this point. Okay. Okay, good. So this picture shows you how to draw, how to think of these two paths. Okay, and now um, so let me erase everything. Now we choose a path f from we choose a path f in x from x0 to x1. Okay, that is f of 0 equal to x0, and f of 1 is equal to x1. Okay, now according to the key facts discussed in the beginning of the proof, okay, um, hang on a moment, what have we shown in the previous uh, slide is the following. we showed that I star I twiddle is path homotopic to E0, right? This is what we have shown. And now F is this path, and we have shown that H from I cross I to I defined by HST equal to 1 minus T I star I twiddle at S plus T times E0 at S, right, is a path homotopy between these two paths. Okay, now using the key facts that we have discussed in the beginning of the proof, it turns out that F composed with H, here you see that F is a map from I to X. Okay, well. Okay, so right, it is going to be a map from I cross I to X, right? Because H is going to take I cross I to I, and F is going to take I to X. So F composed with H is a map from I cross I to X. And the key fact suggests that F composed with H is going to be a path homotopy between F composed with I star I twiddle and F composed with E0. Okay, and by using the second key fact, we can write it as F composed with I star F composed with I twiddle. Okay, now what is F composed with I twiddle? Let's see. F composed with I twiddle at S is going to be equal to F of I twiddle of S, and which is F of I twiddle at S is going to be 1 minus S. Minus S. And this is nothing but F twiddle of S, right? The reverse of F is defined this way. So how did we define F twiddle of S? Remember, we defined it as F of 1 minus S. Let me go back and see. It is given in the statement of the theorem. The reverse of F is given by F of 1 minus S, right? Right. good. I think in the note I have made a mistake. It should be f of 1 minus s. So you have to be careful while reading through the notes. It's f of 1 minus s. Okay, so f of 1 minus s is equal to f twiddle of s. So we see that f composed with I twiddle is equal to f twiddle, the reverse of f. This is one thing. And what is f composed with E0? We have already seen earlier that f composed with E0, well, if you want we can do it again. F composed with E0 at S is f of E0 at S, and E0 at S is just 0 because it's the constant map. So this is f, well, f of 0, and f of 0 is x0 because f is a path from x0 to x1 in X. So and this is the map E sub x0 at S, right? The constant map. So we see that f composed with E0 is going to be equal to E sub x0. So we plug in these expressions here. We see f composed with I is just f because I is the identity map. This is f star, and f composed with I twiddle is f twiddle, the reverse of f. And f composed with E0 is f composed with E0 is E sub x0. Okay, so so let me erase these things. I don't need them anymore. So we have found that f star f twiddle is path homotopic to E sub x0, where the required homotopy is f composed with h. Okay, h was defined earlier. Okay, so now the well-definedness of the product between paths in the respective homotopy classes, let us write the following. E sub x0 is equal to, since they are path homotopic, they belong to the same class, and by the well-definedness of the product between uh, homotopic classes of paths, let us write this: the class of f star, the class of f twiddle, the reverse of f. Okay, so so we have been able to show this: the class of f star, the class of f twiddle is going to be equal to the class of this constant map E sub x0. Okay, so using similar argument, exactly similar argument, one will be able to show that the class of f twiddle star, the class of f, is equal to the class of E sub x1. Okay, so this way we prove part 3. Okay, so let us take a break here. We'll try to prove the associativity part, that is the part 1 of theorem 1, in the next segment. Thank you for attending this segment of the first lecture.